When we think of places you might find life, we typically think of the Goldilocks zone around a star, where water would be liquid in its natural state. And if you get a little too close to the star, heat would evaporate the water and you don't have it anymore, it's gone. Too far away, it would freeze. And neither of those states of H2O are useful to life as we know it. We need liquid water. So you can establish this green zone, this habitable zone, this Goldilocks zone, where if you find a planet orbiting there, hey, there's a good chance it could have liquid water. Let's look there first for life as we know it. Now, it turns out that this source of heat, of course, is traceable to the sun. And as you go farther out, everything would or should be frozen, all other things being equal. But Europa, a moon of Jupiter sitting well outside of the Goldilocks zone, is kept warm. Not from energy sources traceable to the sun, but from what we call the tidal forces of Jupiter itself. So Jupiter and surrounding moons are actually pumping energy into Europa. And how does it do that? As Europa orbits Jupiter, its shape changes. It's not fundamentally different from tides rising and falling on Earth. The shape of the water system of the Earth is responding to tidal forces of the moon. And when you do that to a solid object, the solid object is stressing. And because of this, a consequence of this is that you are pumping energy into the object. It is no different from when you say, anyone who's familiar with racket sports, indoor racket sports, could be a racquetball or squash. You say, let's warm up the ball before we start playing. You want to hit it around a few times. You are literally warming up the ball. It's not just simply, let's get loose. You are literally warming up the ball. How? You are distorting it every time you smack it, and then the resilience of the ball pops it back into shape. And every time you do that, every smack, you're pumping energy into the ball. It's not fundamentally different from what's going on in orbit around Jupiter. So you have this frozen world, Europa, completely frozen on its surface. But you look at the surface and there are cracks in the ice. There are ridges in the ice where there's a crack and it shifted and then refroze. So this ridge has a discontinuity in the crack and then continues in another place. So what this tells you is that Europa cannot be completely frozen, because if it were, nothing would be moving. You look at the surface of Europa, the frozen surface, there are like ice chunks that are like shifted and refrozen and shifted again. It looks just like if you fly over the Arctic Ocean. Fly over the Arctic Ocean in the winter, these are ice sheets that are breaking and refreezing all the time. It's the same signature as that. So all of us are convinced that beneath this icy surface is an ocean of liquid water. And there's no reason to think it wouldn't have been liquid for billions of years. On Earth, where we find liquid water, we find life. So what this means is, not only do we have a source of heat outside of the Goldilocks zone, we have conditions under which life could be thriving. And knowing that this is possible has completely broadened the net that we are casting in search for life in the universe. No longer is it that let's find a 72-degree tidal pond and see life forming there. No, life is pretty hardy. And by the way, Europa is not the only one of these moons in the outer solar system that's kept warm by these sort of tidal stress forces. There are other moons that feel the same influx of energy. So for example, Io, that's the innermost moon of Jupiter, that suffers from this phenomenon even more. And that moon is so hot, there are volcanoes erupting from within. It is rendered molten, whatever solid parts of that moon there are. And so, in fact, the most volcanically active place in the solar system is Io, one of the moons of Jupiter. And We don't know how to sustain life under temperatures that hot. So, but it's a reminder that if you're looking for sources of energy, we no longer need to be anchored to a host star in our search for life in the universe. The question isn't about whether dark matter exists or not. What's going on is when we measure gravity in the universe, the collective gravity of the stars, the planets, the moons, the gas clouds, the black holes, the whole galaxies, when we do this, 85% has no known origin. So it's not a matter of whether dark matter exists or not. It's a measurement. Period. Now, dark matter is not even what we should be calling it, because that implies that it's matter. It implies we know something about it that we actually don't. So a more precise labeling for it would be dark gravity. Now, if I called it dark gravity, are you going to say, does dark gravity really exist? I'd say, yeah, 85% of the gravity has no known origin. There it is. Let's figure out what's causing it. The fact that the word matter got into that word is forcing people to say, well, I have another idea. I bet it's not matter. It could be something else. We're overreacting to a label that overstates our actual insights or knowledge into what it is we're describing. And then I just joke, we should just call it Fred. Fred or Wilma. Something where there is no reference to what we think it is, because in fact, we have no idea. So here's how you actually measure the stuff. In a galaxy, which is the smallest aggregation of matter where dark matter manifests. So you look how fast it's rotating, and we know from laws of gravity, first laid down by Johannes Kepler and then enhanced and given further detail and deeper understanding by Isaac Newton. You write down these equations and say, oh, look how fast it's rotating. You invoke that rotation rate in the equation, and out the other side says how much gravity, how much mass should be there attracting you. And the more mass that's there, the faster we expect you to be orbiting. That kind of makes sense. So when you do this calculation on a galactic scale, we get vastly more mass attracting you than we actually can detect. I'm adding up stars, gas clouds, moons, planets, black holes. Add it all up. It's a fraction of what we know is attracting you in this orbit. And we cannot detect the rest. And so we hand it this title, dark matter. Understandably, I suppose, but it implies that we know that it's matter. But we don't. We know we can't detect it in any known way. And we know it has gravity. So it really should be called dark gravity. I think the over-under on what dark matter might be today, I think we're all kind of leaning towards a family of particles, subatomic particles, that have hardly any ability to interact with the particles we have come to know and love, quote, ordinary matter. And that would make it matter, dark matter, as we've all been describing it. And it's not a weird thing that you could have a particle that doesn't interact with our particles. Within our own family of particles, there are examples where the interaction is very weak or non-existent. You might have heard of neutrinos. This is a ghost-like particle that permeates the universe and hardly interacts with familiar matter at all. Yet it is part of our family of particles that we know exist and that we can detect and interact with. So if we can have an elusive particle that's part of our own familiar family of particles, it's not much of a stretch to think of a whole other category of particles where none of them give a rat's ass about the rest of us, and they just pass right through us as though we're not even there. Now, here's what's interesting about dark matter. We know it doesn't interact with us, except gravitationally. By the way, what do I mean by interact? Does it bind and make atoms and molecules and solid objects? No, it does not interact with us in any important known way. But it also doesn't interact with itself. That's what's interesting. So if it interacted with itself, you can imagine finding dark matter planets, dark matter galaxies. Because to interact with yourself is what allows you to accumulate and have a concentration of matter in one place versus another. These are the atomic bonds and the molecular bonds that create solid objects. And if particles do not interact with one another, they just pass through, you just have this zone of mass, not really doing anything interesting. So dark matter not only doesn't interact with us, it doesn't interact with itself. And that's why when we find dark matter across the universe, it's very diffusely spread out. It's like over here. It's not in this one spot and look at this concentration. No, that's not how that works. Just as a quick example, I was channel surfing, came across a football game that had just ended in a tie. They went into overtime. I had 15 minutes to kill before my movie came on. I said, I'll sit there and watch this overtime period. And I'm watching it, and there's the requisite exchange of possession before you go into sudden death overtime. So they get it to within 50 yards of the goalpost, and so they decide to kick a field goal for the win. And so I'm watching this. It's exciting, right? So then the ball gets hiked, the kick, the ball tumbles, and it heads towards the left upright, careens off the left post, and in for the win. And I said, wait a minute. We have a round ball on a cylindrical thing. So fractions of an inch matter which way this will bounce off of a post. So I said, let me check this out. So I checked the orientation of the stadium, the latitude of the city, and I did a calculation, and then I tweeted. And I said, the winning field goal by the Cincinnati Bengals in overtime was likely enabled by a third of an inch drift to the right, enabled by Earth's rotation. And people say, oh my God, it's blown my mind. Oh, and the local news got it. Everybody got it. Of course you want to know that the rotation of the Earth helped that field goal kick. Because a kick going due north or due south will be deflected to the right in the northern hemisphere. And that's exactly what happened to that kick. And I use that as an excuse to send out a second tweet saying, by the way, we call this the Coriolis force. And that's what creates the circulation of all storms, hurricanes, tornadoes, what do they call them in the Pacific? Cyclones.
Get smarter faster with new videos every week from the world's biggest thinkers.